always a tough situation to put a person in. I'll try to be as quick as I can and share all the messages that I need to share. So my name is Pratap Subramaniam. For the last several years at VMware, we've been trying to answer a specific question that our customers have been pouring at us. Okay, and I'm going to be describing the problem to you all and the various solutions that we looked at and why we chose this particular path and why we think this is the most economically viable path also, right? All right, so let me take some time and actually describe the problem to you all, okay? What we hear from our customers is that they have purchased their systems with 80 cores, 120 cores, whatever it is, and they're finding that a lot of their cores are just not fully utilized, okay? And we heard this for a number of times, and then we actually did some research on this and poked around, and it's a legitimate concern. Most of our customers' data centers are running at like 20 to 35% occupancy, okay? So it's not like 20 to 30% of the cores are the only ones that are utilized. It's like all cores are utilized, but running at 20 to 30% occupancy, okay? Which puts the customer at a very awkward place because a lot of the enterprise-grade software is actually sold by cores. So you actually pay by the core. So if you buy a database, for instance, you pay them X thousands of dollars per core. Now the core is utilized, they got to pay for that core. Whether that core is only running at 20% steam or 100% steam is not part of the equation there. And this is very unfortunate because we are the virtual infrastructure vendor. It's our job to keep the CPUs busy, and we are looked upon as, what are you doing here that's not right? And when we dug deeper into the situation, it was not possible for us to ratchet up the CPU for the same workloads because the workloads needed more memory and the memory was not available, okay? Then we went and looked and said, why is the memory not available? Are you just not like building your systems with the right amount of DRAM on it? Should you just add more DRAM? What's going on here? As it turns out, there is really no memory available. All these virtual machines that get provisioned onto the system, they're provisioned with an anticipation for peak loads. And if you sum up all the peak allocations for each of these virtual machines, they actually do add up to the whole DRAM on the system. So the customer looks at us and says, this is not a very satisfying situation, and moreover, Intel is chomping out more cores every year, and they're thinking of buying bigger, more systems with more cores the next year around, and it's going to sit around with such a low utilization, right? It's really disappointing if you think about it, and all the hard work that Intel does, only about a fifth of that actually gets consumed. They pay for 100% of it, but only a fifth of it's actually utilized. So this is the problem that we are dealing with, okay? And you may look at it and say, well, okay, there's a locked up software licenses, but there's also heating and cooling of all these cores. In the end, it's a total TCO picture that we are looking at and saying, we want to reduce the TCO for the customer. That's the problem here, and that's the direction we are going. Now, the customers have had one of two reactions, popular reactions, okay? One class of customers said, well, if you told me that the memory is the critical resource, I'll add more memory. I'll throw DRAM at the problem, and everything will be fine. Well, everything is somewhat fine. Everything doesn't get fully fine. It goes in the right direction because now more CPUs are being utilized, for sure, but they're paying for the more DRAM. This DRAM consumes more energy, and the power and everything like that goes up, and the TCO, in the end, is not satisfying. Sometimes some of our customers run into, just occupancy problem. Like they just don't have enough spots in the system to put this new DRAM in. They've run out of all the memory channel slots, and they have no additional place to plug a DIMM in. Right? So then they go higher density, and that increases the TCO even further. Higher density DIMMs are significantly more expensive than lower density DIMMs. So they're now, once they go down this path, they end up realizing that, sure, if they want to use their CPU well and their software licenses well, they now have to pay the DRAM vendor a chunk of cash. okay, to make that happen. And they look at us and say, why can't the infrastructure just take care of this for me? Why are you doing this to me, right? So in the end, it all seems like somehow it's VMware's problem, right? So, and a second group of customers have taken a slightly different route. They've said, okay, listen, my goal is not to necessarily run more workloads on the same server. I'll just buy more servers and I'll run more workloads. Therefore, on any given amount of time, I'm satisfying more demand from their own customers. So they'll be able to run more workloads because they just have more servers. But now they have this in the situation, they have to buy more software licenses because software licenses are per core. Okay, so now they have more cores, so they got to buy more software licenses. So they just get caught up in this whole TCO game. Their total cost of ownership for systems has just gone up. All in all, this is not a very satisfying situation to be in, right? You can't solve this problem by throwing more DRAM at the problem or more systems at the problem. You have to think differently here. And that is sort of where VMware comes into picture. We actually spent some time looking at this problem and saying, what is the right way to solve this, right? I mean, you have a situation where you've given your child its own bedroom and stuff like that, and every time you walk inside, you can't even walk inside, it's got all kinds of garbage all over the place. And the kid's asking for another room, okay? Or, maybe build me a bigger bedroom, right? That's not the solution. The right solution is to go off and clean up the space, make it more livable, right? And that's what we are doing with page classification. We are looking at it and saying, well, let's look at the memory. How well are you utilizing it? You got yourself a terabyte of DRAM. How much of the terabyte of the DRAM is actually consumed well? For how long? And stuff like that. And that's where a core expertise inside the group that I work very closely with comes into play. There's an old statement that, when you have a hammer, everything looks like a nail. And, we have a hammer at VMware. Our hammer is that we are pretty good at workload resource management. We think we are pretty good at it, right? And so that's what we did. We looked at it, we analyzed the memory patterns for a wide variety of workloads, not just one or two, but a wide variety of workloads, right? And very prototypical of what our customers would use. No, we're not going to go and analyze something, say, NASA would use or something like that, but we looked at what our customers did, right? The garden variety workloads that our customers used. For that, and then we classified them as very hot pages to very cold pages. And the definition of hot and cold is just frequency of access, whether it's read access or write access, it doesn't matter. It's just the frequency of access. We sorted them based on that and said, the most deserving of these pages, if we just took the most deserving of these pages and kept them in DRAM, and took everything else and kind of moved it out of DRAM, okay, how much DRAM gets freed up, right? It's just like you take the garbage out of the bedroom and move it into the garage. The kid doesn't miss it for another 3 years. You sell it on the in a flea market somewhere, right? So that's the sort of tactic we have taken. So what we have taken, the approach we are going down, is we are not changing the behavior of the IT admin, which is a very complicated problem. If I go to the IT admin and say, why are you allocating this much DRAM to this virtual machine? Maybe you should get better. Maybe I can teach you how to be a better IT admin. That's a conversation that's not going to go anywhere, okay? So we have taken a different approach and said, we will transparently clean up all the garbage that they create on a daily basis, continually, okay? This is not a one-time thing. We have to do it all the time, right? And there's a lot of cost to doing it. It's a technically complicated problem, but that's what we went down, okay? Now, I need you to bear with me on this in this animation here. Basically, what this is showing is exactly what I just described to you. What we do is we dynamically and constantly move pages away from host DRAM that are not deserving to remain in host DRAM. Where do we move it to? Okay, like I said, move it to the garage, right? So it's cheap. It's a place where junk can be held. And we chose a cheaper memory tier. We chose a nice, gigantic SSD to put all these pages in, okay? And it's cheap. It's orders of magnitude cheaper than DRAM. Now we have accommodated the possibility of maybe running more workloads on the free space that's been created, thereby increasing the CPU occupancy, while increasing the total cost of ownership by a very small amount, the cost of the SSD. Okay, plus a bunch of other things. Okay, but it's not like I'm asking you to buy more DRAM. I'm not asking you to go buy another terabyte of DRAM. I'm not asking you to go buy another system. Okay, I'm asking you to buy another SSD. Okay, and I'm going to package it all up nicely with VCF and make it all finally usable and stuff like that, right? That's the shtick here. So what we did was we actually, and I'll show you later in this talk, we were actually able to get to a place where we were able to fully utilize the CPU in the box for several workloads. So this is actually, it actually works. Okay. And we were able to, oftentimes, for most workloads that we have run, we were able to clean up 40% of the host DRAM without the system even knowing. It's all done transparently. You know, you run a virtual machine, you ask for a terabyte of memory for the virtual machine, it doesn't even know that you're doing tiering on it. Okay. The performance is not that much affected. It is affected, but it's not that much affected. So if you're looking at the performance, maybe you'll be able to say, oh, somebody's tiering my memory. But who does that, right? So having said that, I need to make one more point here. So I want to be very clear, the audience to be very clear here. This is not memory expansion. Okay, this use case, the way we are approaching this problem is not memory expansion. It is completely different. The economics here is different. The performance profiles are different. The challenges are different than what it would be if I was building a memory expander. Okay. The requirements for bandwidth will be different in this use case. The requirements for latency will be different. And the reason I'm saying that is because by design, I am only putting cold pages in this location, by design. So if ever a particular page that I have demoted to a cheaper tier suddenly becomes warm or hot, my algorithm kicks in, brings it back into host DRAM transparently. Okay? If it doesn't do that, sure enough, there'll be a performance hit. But it does that. And we have written the algorithm to actually react very, very fast. The whole emphasis on the algorithm, the choices we have made in the design is for the reaction time. It's all about the reaction time. So we don't care about the bandwidth to this device. The bandwidth to the device can be really low, doesn't matter. It could be sipping through an ocean at a straw, don't care. Okay? But the latency is very important. Latency to that access is very important. So we have built the system to react fast. Okay? So that I want everyone to understand that the rest of the talk is not about memory expansion. Okay? It's about solving a problem that a memory expander could solve if it came for free. But it doesn't, right? So, all right. With that, let me introduce at a high level the project. It's codenamed Peaberry inside VMware. That's what everybody calls it. But when it probably goes out, it'll have a more professional name, right? What it looks like is an add-on card that communicates to the host via CXL, which is a low latency protocol. I won't go into the protocol here. That itself is a 45-minute talk of its own. But assume that it serves the purpose that we need, which is good bandwidth, good enough bandwidth at a low enough latency. Okay? We have an FPGA there in which all of our IP that we have written has been situated, and a NIC, and a DRAM, and a couple of SSDs. The cartoon is actually wrong. We actually have 2 SSDs. Okay? And the DRAM is there, and I'll come to why it's there in the NIC. The couple of things that we are trying to accomplish with this introduction of Peaberry is that we want to solve the local memory tiering problem, the CPU occupancy problem, for sure. That's our first goal. But we don't want to embark upon this journey of building another add-on card just for one solution. Okay? It has to be more than that for us. What is it that we are also intending to do with it? You know, we want to do things like maybe access a pool of free memory sitting in another cluster, or speed up virtual machine migration, which is also possible with the implementation that we have. So that NIC that's there by design is going to allow a swarm effect of Peaberries, right? All these Peaberries will talk to each other and kind of do their thing, moving data around when it's needed, but they'll only deal with cold memory. They'll never deal with hot or warm memory. It's only cold memory, okay? So the whole design is towards that, and I'll go deeper into what each of these blocks mean soon. So if we were to build this, right, we definitely believe that we will solve the current question that our customer is asking, which is, hey, my CPU occupancy is really low. But we also see, two possible customer camps that are likely to happen. The first camp of customers, we think, maybe this customer doesn't have a rising demand curve coming into his company. That is, every year the demand that he's trying to satisfy is flatlining. Well, that person is going to say, well, okay, why shouldn't I just buy another machine the next year when I'm going to buy it with lesser DRAM, but with a Peaberry card on it? Makes perfect sense. We're not going to say no to that guy. Okay, we're going to sell the Peaberry card to him, and the person will buy lesser DRAM, okay? But most customers have a rising demand curve coming into their own organizations. They buy more servers every year. They don't buy lesser servers every year, right? Now, we want to educate these people who are buying more servers every year to look at it as a TCO savings play, look at it as a means to get more out of their dollar that they spend on their budget. If they bought an 80-core machine, I want 70 out of the 80 cores to be utilized to 100%, okay? That's the goal. And after that, we expect that people will look at their purchases, the budget that they're spending on infrastructure and say, wow, okay, this is money well spent, and they'll buy more, okay? I would rather put a customer in such a satisfied state where they're buying more computers based on the fact that they realize that the computers that they previously bought are actually well utilized, than buying more expanded memory or this and that and stuff like that to make the system that they previously purchased come to at least mediocre status, right? That's the goal here. So,
what is VCF?
Okay, VCF is the product that VMware sells. It's called Virtual VMware Cloud Foundation, okay? That's a piece of software that you purchase, and then you can take a bunch of machines and turn it into a private cloud, okay? And VMware is going in that direction where we are telling people, all our people, that you can have your own data center and you can run it with the same agility and same flexibility and same all the greatness that you get in public cloud, but you can get it in the private cloud format. That's what VMware sells nowadays, right? So now let me go into the innards of Peaberry a little bit, okay? This is still not very deep, but it's deeper than what I've been speaking so far. Let's start with the lower right-hand corner and then go anti-clockwise in the FPGA, okay? You see the couple of SSDs out there. We like 2 SSDs as opposed to 1 SSD because it allows us to stripe and get better bandwidth, okay? That's a simple reason there. It is not designed for reliability purposes, but it is designed for performance purposes, okay? If you go a little further, you see a bunch of DRAM we actually have in our board today. 32 gigabytes of DRAM, and most of the 32 gigabytes is actually used as a cache to cache some of the pages that are sort of still not figured out whether they're cold or warm, and they're kind of oscillating between those two states. We keep them in the DRAM cache, okay? And we could make that cache bigger, but we don't see the reason today. The SSD's total capacity is about 4 terabytes, and 32 gigabytes seems to be pretty good for caching in front of 4 terabytes for all the workloads that we have run so far, right? We have a 100 gig NIC, which is not by any stretch of the imagination the fastest NIC that's nowadays people are bandying about, but it's pretty good for our customer base, okay? Most people in our customer base are still playing around with 40 gig NICs. So 100 gig NICs for them is pretty good, and we think we can do future use cases such as virtual machine migration and things like that very effectively with a 100 gig NIC. Then comes the FPGA, and what we have done is we have offloaded pretty much all the activity that we used to do on the Xeons to do page classification and so on, which takes CPU. Okay, we got to observe access patterns and all that stuff, and that takes a bunch of CPU. We have offloaded all of that to some way cheaper ARM processors that are sitting on the FPGA. Okay, and we have taken the rest of all this logic of determining, what page in the DRAM cache. Let's start from the right-hand corner. Say you're sitting in the DRAM cache, a page is sitting in the DRAM cache, and you start seeing a whole bunch of CXL.mem accesses coming to it. We then say at some point, you probably should not be in the cache anymore. You should probably go back to the host, right? So we initiate a DMA transfer at that point in time automatically from the DRAM cache to the host. You situate him in some place in the host, and then we go and muck around with the TLBs and the page tables to make sure that the guy points in the new location, right? All of that logic is in the FPGA. Okay. Similarly, the logic to actually move a page from the host that has now become cold into the DRAM cache is also on the FPGA. So the demoter logic and the promoter logic is all in the FPGA. The ability for the FPGA to observe the host memory, to see what is becoming hot, what is becoming cold, what is the frequency, is it more permanent, is it kind of transient, all of that stuff happens through the CXL.cache, and we actually use the CXL.cache to observe the host. How all of these things happen is sort of internal information, but I can't talk about that level of detail here. But we barely run anything on the host anymore. This is still a small representation of code that actually runs on the Xeons. But our goal with this whole journey is to free up the Xeons for the guest to utilize. So in this journey, we are not only attacking local memory tiering, but we are also starting to offload the hypervisor away from the Xeons and freeing the Xeons more and more to the guest. So when Peaberry does go out, there will be a bunch of things that it shows off as its value proposition. It's sort of future-proofed with a lot more use cases. It's also going to be offloading the hypervisor. It's also going to solve the local memory tiering problem pretty thoroughly. That's the goal, right? Now, the logic to manage the 100 gig NIC is also on the FPGA. The logic to manage the traffic from the SSD cache to the host DDR5 is also in the FPGA. There is also another loop that's very private to the FPGA where pages go from the DRAM cache to the SSD and sometimes from the SSD back to the DRAM cache. There's a little loop there. So one thing you need to realize is that this stuff happens all the time. This is not a static determination. It's not like at the beginning of the virtual machine's life, someone says, this portion of memory is cold, this portion of memory is hot. No, that's not the case. It's like constant. So if you actually look at the system, there's pages going from the host to the card and back, and there's a flow of pages continuously happening. Several megabytes per second keep going back and forth. Okay, so, and as the application, say if you're running an Oracle workload or Oracle database, it could change phase. All of a sudden, you could say the database suddenly wakes up and starts doing a bunch of work. Then you'll start seeing this flow pick up. Some things that we thought were cold before are not cold anymore. They start moving back to the host. So this flow is something that we work very hard to make very, very efficient. It requires, like I said, a bunch of DMA activity and also mucking around with the TLBs and page tables and so on, right? So once again, this is a cartoon of the Peaberry card. The key features that I want to highlight at this point are that since we are using CXL.mem to access the pages that are on the Peaberry card, okay, there are no page faults. This is not a situation where, like swapping, where you would move a page into a hard drive somewhere, and then you will let the system take a page fault, and then from within the page fault handler, you go issue a DMA operation or an IO operation to bring the page in, map it, and all that stuff. That's not how it works. Okay? We use CXL.mem. So if a page is accessed, the access goes through all the way to the SSD. We have rarely seen that happen because our cache catches it. But it does happen. Okay? The reason why we went down that path, as opposed to letting it take a page fault, is because page faults are expensive. Okay? Who designs a processor in which the page fault is not an exception condition? It is an exception condition. By design, it's expensive. Okay? And we don't want to fall into the trap of using an expensive tool on a path where it's like 50 megabytes of data going back and forth all the time. That'll just make us not very reactive. And being fast in reaction time is the primary goal of this device. Otherwise, we could have just used a swapping technique for this problem, right? There's no innovation at that point in time. So CXL.mem, the fact that we are taking 0 page faults, all help us in making this application or making this tool applicable for a wide variety of workloads. I don't believe we will actually have a statement where we will say, oh, if you're running this particular workload, don't use Peaberry, or if you're using this workload, then maybe Peaberry is a better fit. We won't be making such statements when we actually go out into the market, right? Also, because of the fact that we don't take a page fault, we don't fall into this trap of getting the virtual machine descheduled while the page is brought in and so on. The virtual machine is stuck waiting for the page to come, okay? So we made that design choice consciously because we didn't want jitter. Anytime a virtual machine gets descheduled, it takes several hundred of milliseconds later for it to come back and get scheduled again. That adds up. You know, if you do that 1,000 times in the lifetime of a virtual machine, it starts showing in jitter. Transactions take longer in the guest and so on. So we didn't want that. We also believe performance-sensitive workloads will work very well with our implementation. Now, all this is about performance. You know, the team has also worked very hard to make sure that this board is automatically self-managed. It is the bit stream for the FPGA, anything that is needed for the SSD management, the BMC, everything is packaged into ESXi image. So when someone installs VCF, they get the ESXi OS software. When that OS boots the host, it scans, figures out that there's a Peaberry card, slaps the right firmware on top of it, and takes care of everything. The card is completely stateless. From boot to boot, it has nothing on it that matters for anybody, right? So we have taken care of making this card as transparent to the customer as humanly possible. When a patch or an upgrade is done to the VCF software, that's the only opportunity you get to upgrade or patch this device to. You don't get to do upgrade or do anything to this device sort of a sideband way. There's only one front door to actually do any of these updates. And there is no add-on license. If you purchase VCF, you get to use Peaberry cards. Okay? You don't have to get another add-on license to activate the ability to use Peaberry or anything of that nature. And we are releasing, we are going or planning to release with a 4 terabyte capacity, which we think is a big enough capacity for our customers to run a wide variety of workloads and just not run into another wall, right? So that's sort of where we are right now. And like I said, this is not a one-trick pony. You know, we want to go out and do a very good job in solving the local memory tiering problem. That's definitely a goal. But we also think that subsequent to that, we will be exploring maybe tiering to a remote node, or maybe tiering to a remote device. And we also think some level of optimizing one of our most popular features in our customer base, which is virtual machine migration. We think we have a very good chance to optimizing the virtual machine migration latency to the order of maybe even doubling the, or reducing in half the latency of doing a migration of a virtual machine. And that's pretty huge because thousands and thousands of vMotions happen every day in every customer that we have, right? For just load balancing across the cluster and so on. And so if that can be maybe double, you can do twice the amount, that actually means a lot to our customers, because for one simple use case, I can tell you now, if a person wants to upgrade a particular host, say it's a 2 terabyte host, it's running 40, 50 virtual machines on it. They have to vacate all those virtual machines to another host. And then they upgrade that host, and then they bring all the virtual machines back. This happens all the time. People are upgrading ESXi all the time in our data centers. If you make that process twice as fast, they can apply patches faster. It just makes their operational efficiency better. So we hope to go down that path. Oh, I'm sorry. And there's one additional thing that I want to talk about, is that we have been in another pocket inside our company sort of thinking about how can we utilize this FPGA that we are injecting into our customer base better. For what other use cases can we utilize it? Right now, with all the RTL that we've written for the local memory tiering project, we still have a bunch of FPGA space left and space in the SRAMs left. So we do hope to maybe put some inferencing or whatever else our customers might want into that space and take it along and see whether that makes sense to our market. Okay. So nothing that I've said here is just VMware. Altera has been with us almost since the beginning, several years ago, even before the CXL came along and was popular. We were working on this thing with UPI at one point. Samsung has been very helpful. Inventec has been very helpful in Bitware. They've all manufactured boards for us. Let's talk about some performance results. Now, does this actually solve the problem that I outlined in the first slide? Okay. So on the left bar there, let's say you have a machine with 2 sockets, 40 cores per socket, very typical for our customer base, 2 socket machines, and it has a terabyte of DRAM. Okay. We're running this benchmark called VMmark, and the way VMmark works is it has what are called groups of virtual machines. These are virtual machines that do a variety of different work. They could be databases, they could be web servers, bunch of other activity and stuff like that. And they measure by running all the 19 machines in every group, and the group is called a tile. So they run many, many tiles, and your VMmark score is if you're able to run n tiles and n plus 1th, when you add n plus 1 tiles, if there is some quality of service failure. So any one of the VMs in any one of the tiles, if it registers a failure in its transaction, that means the n plus 1th tile failed. That means your VMware score is n. Okay? With that explanation, we were able to run 3 tiles on the 1 terabyte host with 80 cores on it. So that's 3 times 19, you're talking 60 virtual machines running, and we are tiering this thing up the wazoo. I'm sorry, we were not tiering at all on the left-hand side. So that's the baseline comparison. This is what a customer sees when they're just basically having a 80 core machine with a terabyte, and they're running some workload, and this is what they're seeing, right? They're able to run 3 tiles. We took that machine, same workload. All we did was we injected a Peaberry card into the system. Okay, no changes at all, just the Peaberry card. And the Peaberry card had 4 terabytes of capacity in it. And then we ran the system, but we activated memory tiering this time. We were able to get 6 tiles. 6 tiles on the same machine with 1 terabyte of DRAM, when we previously could only get 3 tiles. Okay? And that means those 6 tiles actually worked. There were no quality of service failures. So the performance hit that we gave to these workloads was so minimal that the benchmark didn't even realize that it was being tiered. That's the point, right? And we didn't even use all the 4 terabytes. We used about 1.31 terabytes. That's not 1.25, it's actually 1.31 terabytes. It's a typo of the 4 terabytes. So we used 1 terabyte of host DRAM, 1.31 terabytes of Peaberry memory, which is not real memory, it's cold storage, okay? And we were able to get twice the productivity from the data center. That's the way to think about it. So for the price of a Peaberry card, today, the customer can double their productivity. Okay. Okay. Then we ran some more workloads. On that green bar there is a Redis benchmark, which is an in-memory database. And we ran it with a 3:1. That is, for every 3 bytes of host DRAM, we gave it 1 byte of Peaberry. So we were able to squeeze out 25% of host DRAM on that in-memory database, which is a very memory-intensive workload. If you guys have studied the Redis benchmark, the heat map is across the board. Like every page looks hot. So it's remarkable that we were even able to squeeze 25% from it. And it's a testament to the reactiveness of the algorithm. That is, when it sees something is getting hot, if it's sitting in SSD, it pulls it back into the host really, really rapidly. That's how we were even able to squeeze 25% of Redis. The other workload that we ran was a more garden variety database, SQL database. A lot of our customers use it. And we were able to squeeze a lot more. We were able to squeeze 50% out of that database. And these are all databases that were not provisioned in a silly manner. They were provisioned in a manner that they were already memory pressured inside. So we configured the workload to actually be having an active working set that's above normal for our own customer base. Right? And we still got this much performance out of it. So what I'm trying to say with this slide is that you give up 10%, 5%, you'll get back a lot with memory tiering. If you don't want to give any performance back, it's going to be a tough problem. Okay? But memory tiering in general, because of all the data transfers that are going on, the TLB activity that's going on, by nature is going to reduce your performance. The key problem here is how do you reduce it by no more than a certain amount and still maintain a good TCO for the customer. Right? So far I've showed you that performance looks somewhat acceptable, right? In some cases, actually very good. We have a demo that Arvind, who's the product manager for this project in VMware, will be showing in the demo booth. I encourage you all to go there and kind of ask him tough questions. And you can also see the actual boards.
Altera, accelerating innovators.